All right, welcome back, Marauders. This video 5.4, enthalpy of reactions. We're going to talk about how energy in the form of heat is released or absorbed during chemical reactions. So many chemical reactions release or absorb heat as they occur. We can think of a couple examples, simple examples, any kind of combustion reactions. Think about just a candle burning. That's a chemical reaction. You have the paraffin, which is reacting with oxygen, and chemical bonds are being broken, new ones are being formed, and that reaction would release heat. Ones that absorb heat, not quite as common, but probably the best example is like a chemical ice pack. Those chemical ice packs that you have in first aid kits, you crack them open, the two chemicals mix, and as they react with each other, they absorb heat from the surroundings and therefore feel cold. So a lot of chemical reactions include absorbing heat or releasing heat as they occur, as chemical bonds are formed and broken. Enthalpy changes or energy is usually transferred. We're, like we said earlier in the chapter, not really going to deal with work being done very much. We're going to deal mainly with just heat or enthalpy. So the enthalpy change that occurs during a chemical reaction is called the enthalpy of the reaction. Okay. The enthalpy of a reaction can be found if you know how much heat energy is in the products, and you subtract that from how much heat energy or enthalpy is in the reactants. So whenever you see the delta, remember that means change. So delta H means the change in how much energy the products have versus how much energy the reactants had. So it can be positive or negative. If it's positive, it means that we are gaining energy, that the products have more energy than the reactants did at the beginning. And if it's negative, it means it released energy and the products now have less energy than what the reactants had at the beginning. So enthalpy changes are dependent on the amount of reactant used. All right, so we always want to specify how much of the reactant in either moles or grams is being used when we specify an enthalpy change. If you burn a candle, how much heat is going to be released? Well, it depends how big the candle is or how much of it you let burn. If you let just 1/10 of a gram of the candle burn, you'll release some heat. If you let 100 grams of the candle burn, you're going to release a lot more heat. So just like any kind of chemical reaction, the amount of product you produce depends on how much reactant you use, just like we learned in stoichiometry a couple chapters ago. If you reverse a reaction, the enthalpy change has the same magnitude, but the opposite sign. So what does that mean? If we have a chemical reaction that we know releases heat, okay, so as you go from reactants to products, it releases heat, but then we reverse the reaction and we put what was the products are now going to become the reactants, and the reactants are going to become the products. So if we flip the reaction around, the enthalpy change will be the same magnitude, so it's the same size or the same numeric value, but it has the opposite sign. So instead of being positive, it's now negative, or vice versa. And then enthalpy changes depend on the state of the reactants and the products. So this is physical state, like solid, liquid, gas. The solid, liquid, and gas form of every substance has a different amount of enthalpy or energy stored inside of it. So you need to just pay attention to if it's a solid, liquid, or gas when you're doing your calculations and making these decisions. All right, so we have two types of reactions. This is really important, endothermic and exothermic reactions. So we'll talk about exothermic first. Exothermic, probably a little bit more common, easier to think about examples, really easy to think about. Any kind of combustion reaction is always exothermic. So if you have a system, like let's just say it's our candle again, the candle is going to be giving off energy in the form of heat to the surroundings. So the system is whatever we're surrounding, in this case, the candle, like the wax that makes up the candle. And then the surroundings is everything else. So it's the room that we're in or the entire universe. It's the surroundings. And so energy is given off from the system to the surroundings. And so you have a delta H that is less than 0. Enthalpy changes for exothermic reactions are negative. Really important to remember that. It seems a little bit backwards because you'd think, oh, it's a hot reaction. It's giving off heat. And delta H is going to be negative in that case because from the perspective of the system, the wax, the molecules that are reacting within the wax have less energy. They've released that energy to the surroundings, so it's negative. Here's what we call an enthalpy diagram for an exothermic reaction. So this is another exothermic reaction. This one is the reaction between hydrogen and oxygen to form water. And this reaction is going to produce heat. So anytime heat's a product, it's exothermic. And so here's the amount of energy that you have in your reactants. So in hydrogen and oxygen, you have a certain amount of energy, and it happens to be right here on this graph. And then as the reaction takes place, you have your products over here. And your products, as you can see, have less energy than the reactants. Well, that energy had to go somewhere. You can't create it or destroy it. So you are releasing it to the surroundings. And as you can see here, the difference between this height on the graph and this height on the graph is the change in internal energy. And so this is delta H. Okay, so you can see in an exothermic reaction, delta H is negative. It's less than 0 because we have less energy in the products than we did in the reactants, and that has to go somewhere. It's released to the surroundings. Here's endothermic. So endothermic is the opposite of exothermic. Again, not quite as common, but think about like an ice pack. As those two chemicals mix, okay, so the system is your ice pack, and there's a couple different chemicals in there. As they react, chemical bonds are broken, new ones are formed. They're going to absorb energy from the surroundings, and these are going to have a delta H that is greater than 0. It's going to be a positive value because from the perspective of the ice pack, the chemicals inside there now have more stored energy, more potential energy, or more chemical energy. And so it took that from the surroundings, and that's why the surroundings got colder. So like if your hand is next to the ice pack, your hand feels colder because the ice pack took energy away from your hand. So really important to know the difference between endothermic and exothermic. Here's an enthalpy diagram for an endothermic reaction. So an endothermic reaction, I actually have the same reaction that I wrote earlier, but now here the hydrogen and the oxygen are on your product side and the water is on your reactant side. So we flipped the reaction we saw last time. And so now you can see that heat is a reactant. You need to put heat in, you need to put energy into water in order to break those chemical bonds and make it into hydrogen and oxygen gases. So here you can see my delta H is positive because this is how much energy the water had. This is how much energy your products, the hydrogen and oxygen, have stored inside of them. And so it's a gain of energy. And so that's why delta H is going to be positive anytime you have an endothermic reaction. This one's endothermic. So enthalpies of reactions. Enthalpy of reactions is usually written out like this. So usually rather than writing like heat as a product here, we write delta H, and then there's some number. So this is a thermochemical equation because you have the chemical equation, and then you have the thermo part, the part that's about heat over here to the right. And so like we said before, enthalpy change is the change between how much enthalpy the products have minus how much enthalpy the reactants have. And so in this case, we can see there's a decrease in enthalpy. These had more energy than this has. That energy has to go somewhere, so it's released to the surroundings. Anytime you see the negative sign right there, we know it's exothermic. Okay, it's an exothermic reaction as soon as you see that negative sign. So this is a reaction that is like a combustion reaction. If you put your hand next to it, it would feel hot because it's releasing heat. All right, so this is going to be like a stoichiometry type question because it says how much heat is released when 0.1 gram of hydrogen is burned. All right, so we have 0.1 gram of H2, and it's going to be undergoing this reaction, burned in oxygen. And so just like we've done in stoichiometry in the past, when we start with grams, we want to change that into moles because our equations are in terms of moles. So we'll use the molar mass of H2, which is 2 grams of H2 for every 1 mole of H2. And then we'll look at the mole ratio. So typically, you're going to have the moles of hydrogen down here. It'll be 2 moles of hydrogen, right? We want those to cancel out. And then typically right here, we'd put like 2 moles of water if we want to see how much water is produced. But in this case, we're not interested in how much water is produced. We're interested in how much heat is produced. So instead of putting the water, we're going to put the amount of heat. So negative 483.6 kilojoules of heat are released every time 2 moles of hydrogen react. So whenever you see a thermochemical equation like this, the value you have here in kilojoules is for 2 moles of hydrogen, 1 mole of oxygen, and for 2 moles of water being produced. So you can do stoichiometry, right? The grams of hydrogen cancel out, the moles of hydrogen cancel out, and in the end you're going to get kilojoules of heat, and this comes out to be negative 12.1 kilojoules. So it's negative, that's telling us that the heat's being released. You can do that either way. You can show it with the negative sign that it's being released, that it's an exothermic reaction. In a problem like this, you could also just say 12.1 kilojoules are released. That's what the negative sign is telling us. If it were an endothermic reaction, you'd do the process exactly the same. Just the sign here would be different because it's absorbing that amount of heat. This is also an example you can see where if we had more hydrogen, if instead of 0.1 grams we had 10 grams of hydrogen, we're going to have more heat being released. Okay, so it just shows that the amount of heat release is dependent upon how much of the reactant you're using. Lastly, this is just an example of showing how if you reverse a reaction, the enthalpy change has the same value, same magnitude, but has the opposite sign. So here's our reaction again that we looked at earlier with hydrogen and oxygen making water, and negative 483.6 kilojoules of energy are released. So this is exothermic. And if we reverse this, so this is the same reaction, we just move the water over here, and we move the hydrogen and oxygen over to the right side, to the product side. You still have the same value, it's still the same change, but this is now an endothermic.